honor for me to be here, to present here. And thank you again for organizing the seminar. So I not speak about my affiliation because Professor White already mentioned this. I will speak about parametrically excited system. This is the logo of our lab, which is deep array etched in silicon. We have another one in polymer, nano imprinted, but this one I think it's from silicon. Before I start, in this talk I will cover several of our works on parametric resonators. I would like to acknowledge former students and collaborators, and so some of the students who were involved, and specifically Yuval. He's now in Apple. He actually was co-founder of a startup. He was sold recently to Apple for $650 million. So Yuval is living examples that you can really make money out of MEMS. And other students, they work in industry, on academia. Asaf recently got a job in Ben Gurion University as a faculty member. And collaborators, first of all, I would like to mention, of course, Dr. Rob Ilek, that is my long-term collaborator. He's currently in NIST and was previously in Cornell. And Professor Alan Zender, who actually was my sabbatical host, and last month I spent in his laboratory doing measurements, as partially also in this kind of devices. I would like to say a few words about our university, Tel Aviv University. It's a relatively big university of about 30,000 students, and it was founded. It's not so old, but it's relatively old by Israeli means. It's founded as 56, and I am personally from the School of Mechanical Engineering, and our Faculty of Engineering, we have 100 faculty members, and we are ranked something between 51 and 75 in 2015 by Shanghai ranked. I'm in Faculty of Engineering. What is interesting to mention is that Tel Aviv University holds number 22 in the world by number of citations per faculty member, that we write a lot and we are cited no bad. And also, which is pretty interesting, that we are number 9 in the world by amount of VC capital raised by faculty members for different initiatives. And only now faculty engineering, we have several persons, they collectively raised billions of dollars for their startups. They successfully sold or acquired by biggest companies like Texas Instruments, Apple, Google, and so on. And at now School of Mechanical Engineering, it's pretty multidisciplinary, so we have different areas starting from solid mechanics and elasticity and composites, classical, hardcore solid mechanics, and up to environmental engineering and energy systems. And I work in the MES, which is somehow multidisciplinary area. So all this fits into our School of Mechanical Engineering. This is you shot of our university. It's very green. You see students on the grass. It's very hot around the ear. No snow, no rain practically. So it's very nice. It's a very nice area in Tel Aviv. Now about the talks, that what I'm going to do, I would like to say a few words about resonant MEMS and the parametric resonance. I guess it's probably known, but in any case I would like to introduce you concept. After that I will speak about parametric excitation and microstructures in general, and specifically I will focus more on this arrays of microoscillators. It's relatively new activity for us, and we continue to work on this, and I work on this in my sabbatical, continue to work on this in NIST, so it's some directions that I really interesting to advance, and this is outline of the talk. Now, as you probably know, most of MEMS devices are resonant devices. I will not speak about applications, market, and so on, but I just will say that largest part of the devices that you find in every application, starting from cell phones, are actually resonating. Accelerometers, gyros, sensors, most of them, if they are mechanical, I don't speak about pure electrical, pure biological sensors, but if there is something mechanical there, it's usually dynamic and not static in most of the cases. So this area of resonant and MEMS, it's very, very important and broad, and is developing. But also from a scientific point of view, here, at least in Professor Ghost's group that I was lucky to see today, presented by his student, all those biosensors, another approach to do this by nanomechanics, just by measuring resonance frequency, instability, and so on. And these are just several examples of our work, mainly with Rob Ilek from Cornell, about biosensing and mass sensing using this nanomechanics. So basically you have a resonator, you excite it, you measure the frequency, something sticks to it, the frequency changes. You can measure the change in the frequency, and you can know what sticks to it and characterize it some way. This kind of devices could be used not only as sensor, but also as some kind of scientific instrument, because personally I consider MEMS not only as pure applicative area, but also some kind of experimental platforms that can use it in order to do other science, physics, material, characterize material property, and so on. This is just very briefly an example of the work that we did about characterizing of material property of atomic layer deposited very, very thin films. And the point is, when you measure something by resonant method, you cannot measure simultaneously Young modulus and density, because the frequency is a ratio between two. So you can measure one and know in advance the second, or vice versa. So what we try to do to see how we can measure both. So what we did, if you consider some simple cantilever and you have frequency which is out of plane, this direction in plane, we have two modes. We measure the frequency, and they depend on stiffness. So this B is stiffness of the device, and the mass, this is density of the device. If it's single crystal silicon, this is known. Both Young modulus and density is known. After that, if you cover it by a very, very thin LD layer, which is conformal, we measure this again. So this effective stiffness and the effective mass now affected by both. Now, by calculation, the ratio between this frequency before deposition, after deposition, for two modes, out of plane and in plane, for the same beam, we actually have two equations, so we can extract simultaneously Young modulus and density for the same experiment with the same boundary conditions, so all the uncertainties are cancelled out. And it worked very nice, and we were able to measure hafnium oxide density, Young modulus, aluminum oxide, and so on. A very, very thin field, few nanometers thick. It probably could be extended to biolayers. I know that you have some activity in ALD, so this is one of the approaches how we can use resonant nanomechanics as a kind of scientific tool. Right? Parametric excitation. In all these resonant MEMS, usually question arises how we excite them. So we can excite regular linear resonance, and most of the work actually till today is mostly this approach that people use. But there's also another kind of dynamic behavior. One of them specifically I would like to address is parametric resonance. So what is parametric resonance? It's just some background information. If the best way just provide some examples. So if you have a pendulum which is suspended like this, so you shake it in the horizontal direction, it gets excited by inertial force. And you have the equation of motion, which is actually practically depends on the eigenfrequency of the pendulum and forcing, right? And this equation has constant coefficients. So omega is constant because the pendulum has prescribed length and prescribed mass, and this is a forcing term, okay? But we can excite this cantilever a totally different way. We can shake it up and down, which is almost the same, but practically totally different, because in this case, we have the equation of motion which has time-dependent coefficient, and nothing here. So this forcing enters into the equation not as a forcing term, but as some time-varying coefficient. And actually, we think about it, most of the, at least biological systems, they are parametric because their properties depend on time. Maybe not as fast as to excite parametric resonance, but in many cases, at least in biological systems, things change in time as they affect properties and not forcing. Right? So this is classical Mathieu equation of parametric excitation, and it has basically this inertial term and this stiffness term, which it depends on time because there is this cosine tau, which is, and this is canonical equation of parametric excitation. Now, how this behaves? Because equation actually homogeneous, so we don't have forcing term. It behaves in some strange way. If we excite it from totally zero initial condition, nothing happens because we don't have any forcing term. If we have some small non-zero initial conditions, and we have certain combination of this static stiffness and this time-varying stiffness, the behavior depends on the ratio between two. For some ratio, just this initial condition decays. If you have the same pendulum, for some combination of frequency and amplitude, it will just decay, and it will be dead. Right? But for some other combination of parameters, even area of these parameters, epsilon and delta, it starts to diverge, and at least in this equation, it theoretically will diverge up to infinity. Okay? And all this behavior depends where we are in terms of these two parameters, which are both depend on mainly frequency and stiffness. So this area of instability, U is for unstable here, it's called parametric resonance, so I use this abbreviation PR. And there are many, many regions, actually infinite number of regions between these two parameters where we observe this kind of behavior. This is, of course, all this is textbooks materials. Specifically, it's from Rand book, but it can be found practically in any book of nonlinear dynamics. For nonlinear case, if you add some nonlinear term, because in nature, you know, in reality, nothing is linear. So at some stage, everything which is linear starts to be nonlinear, sooner or later. So if you add some nonlinearity, the amplitude is bounded, and we have this very typical time dependency. So this is time, this is displacement. We have this exponentially growing response. After that, it's constant. And from the resonant point of view, if you look at the amplitude as a function of frequency, we have this very typical parametric curves with this jump. So the amplitudes actually grows spontaneously very, very quickly before it reaches this steady state area. Another important point that I'd like to mention in this background part, that if you have some damping in the system, and this is mentioned by Red, this parametric resonance, it doesn't develop for very small amplitude of modulation. It should be higher than a certain value, and this is called parametric threshold. It's in order to excite this kind of oscillation, this excitation of this same pendulum should be higher than a certain value. If it's too low in damped state, it will not be excited. Okay? And I will use this threshold point later in this presentation. Okay, so now how we can realize that except of this pendulum? There are many approaches in mechanical engineering as well. Developed opticians use this all the time. So one of the approaches is just to have a string to pull it periodically, and you can excite vibrations. Here is a string attached to the tuning fork, Camerton, and you can excite vibration like this. It's one of the recent work about excitation from Bucher and his student about excitation of these vibrations. Or you can take a cantilever and shake it up and down. It works more or less similarly to pendulum, so it's a mechanical way to excite it. This approach is used very, very broadly by mechanical engineers in science and in practical engineering. Okay? Another way, actually, we can change the mass and not only stiffness. So if you have a pendulum, we just swing this mass up and down. You can excite vibrations in this way. So you can vary in time stiffness, or you can vary in time inertia. You can vary in time both. This all ways to excite parametric excitations. And about this mass excitation, it was somehow less explored, at least in NEMS area. So we did some work about this excitation by mass. So without going into formulas, if you have a disk, if you have two small masses, and you move them periodically, you can excite vibration by this way. Right? And everything is fully compliant here. There's this mass attached by springs. So we did some work, the theoretical work, which is published in Sound and Vibrations, on this mass excitation. Again, I go through this very briefly just to give some background. And this is an example of response of this kind of device, which is excited by mass modulation and not inertial modulation. I currently have a PhD student working on this, trying to build this kind of device. It's on final stage of fabrication, and I really hope to be able to demonstrate soon this kind of actuation by mass variation of this kind of device. Right? This actually mass variation I used in very routinely basis by children. And this example of this mass variation, and this is actually parametric excitation, because as this swing, what happens, you see the baby, he doesn't move. And he needs his mother or grandmother to push him to excite the oscillation. This is harmonic oscillator. And this girl, she moves her legs and her body to change the mass, moment of inertia, so she doesn't need anyone to push her. This girl, by chance, my daughter, right? And this movie was especially taken by another daughter who is in movies, so it was professionally made. So this is an example of parametric excitation. I even filmed this movie, did some image processing to see how this resonance evolves with time. I don't present it here, but it was done. So this is an example of some kind of parametric system based on mass variation, which is, of course, very known. Now, if you go back to NEMS, how we now implement this nice idea, and what is nice is this parametric excitation that's very efficient. You can reach really large amplitudes with very small amount of energy because you change the parameters of the system. It's very, very efficient, and it's very attractive for application to use this. It could be several approaches. If you want to shake, for example, the mass similar to shake the pendulum, it could be done. This is very nice work. You have double clamp beam here, cantilever here, an electrode. So you basically shake this beam, and you shake this cantilever inertially, which is analogy of this cantilever on a shaker, which people do in macro engineering. And this is another work that we did some time ago. There's some kind of actuator. This is tilting plate, but it's mostly the same. We shake it forward and backward by electrostatic force. There is comb drive here, and this plate starts to tilt up and down. And we measure it. It's not typical parametric response because we were below the threshold due to damping, but still it is a way to excite this device by mass modulation, by this kind of kinematic excitation. Now, another approach is to mimic the stiffness modulation, and the most common approach which is widely used today, and there are review papers on this that I mentioned them, is to use electrostatic stiffness. It's largely known, of course, that electrostatic force could be considered as some kind of effective spring, specifically negative spring. Because it's very easy to change the electrostatic force by modulation voltage, you can change the spring constant, and you can excite devices parametrically. And there are pretty few works about this. So from the most basic level, if you have a parallel capacitor with two electrodes, the equation of motion is like this, and this is electrostatic term. It's easy to see this time dependent because this voltage is time dependent. And this parameter depends on the geometry, area, that doesn't matter too much. But we have this voltage here. So if you change it in time, we change the stiffness in time, nothing here. The minus sign here says that the stiffness is negative. The spring is negative. So we reduce the stiffness and not add the stiffness. And if you normalize it, linearize it, we practically get the same Mathieu equation where you have inertial part, stiffness part, and all this time varying stiffness which basically depends on 2 scale in frequency because the voltage is square. But it is basically pendulum with time-dependent stiffness. And again, there's a lot of activity in this area. There are classical seminal work on this, and to that one to mention, there is a review paper by Jeff Roth, Steve Shaw, Kim Turner about this parametric excitations. It's a very comprehensive paper. And the Lifshitz and Cross also did something, some review paper related to use of parametric resonance in physics to realize it in real life. Not just to have this plate and spring, but to see how we do this. It's very simple. We can put cantilever or double clamp beams between 2 electrodes. You excite it, and you, yes?
Quick question.
Yes?
Is it possible to interpret some of these experiments where people trap beads in laser traps where they can adjust the laser excitation as a kind of stiffness modulation?
Yes, definitely. In optics, it's very developed. People use so-called parametric pumping all the time. So once you have an equation, one of the coefficients which is time-dependent, it could be related to the optical field or mechanical field, definitely. In optics, it's very developed. Definitely. The question is yes. Okay, so we have beam between 2 electrodes. Again, I'm not going to do all the details of the equation here, just if have it here, but it's basically equation of the beam, right? So you have the inertial term, damping, bending stiffness, nonlinear part, and this electrostatic term, which is time-dependent part of it. Okay, and it's easy to realize them. That we have, for example, on a SOI wafer, 2 electrodes, a beam. It's look like this, and you can excite it parametrically, and you can sometimes. What is nice, by the way, in this parametric excitation, that at least as a pendulum, usually pendulum is stable in this configuration, right? At instant stable like this. If you put the pendulum like this, it turns back, it revolves. But if you start to shake the suspension point some certain frequency, in certain amplitude, some region, it could be actually stable and stay like this. So it's statically unstable, but dynamically stable. And these experiments first were done at the beginning of 20th century. But what we did here, we just used this effect to do the same in MEMS. Because here, if you have the voltage on the electrode which is above pulling voltage, it will jump to one of the electrodes. But it turned out that you superimpose some very small amplitude IC drive on this electrode, you can stabilize it, and you can apply the voltage which is above the pulling limit. And this is the result. So you have this is the frequency, and this is the AC voltage, and pulling here above the voltage above pulling voltage. So this point is mapping from experiment. So within this area, you actually could be stable, and it could be good for sensors, for addressing by frequency, and so on. But this is classical parametric behavior, which just was demonstrated also on the micro scale using electrostatic force. Now, with electrostatic force, one of the problems that this is actually a very generic problem in all electrostatic waves, that the force decreases with the distance square. So if you are very close, the force is big, but there is an instability and there is not too much room to move because you're close to the electrode. If you take electrode apart, you have more room to move, but the force is very small. And this is a generic problem which is not easy to overcome. So other approach to overcome this somehow is just to use the stiffness modulation just by pulling the string. Now with string, when you pull it, also you cannot pull it too much because it becomes very stiff when you pull it. So what we did is just break it into 2 parts. And we took like two beams connected to, it's very mechanical actually. You have 2 beams connected by a link, it's very rigid frame, so it actually can move like this. But in this case, because this motion is not constrained in the axial direction, it can move a lot. And it's possible to achieve huge amplitudes here without any comb drive, and this gap could be very small because it moves along it, not toward it. And so we use the model. So again, I probably not go into all the details, but the equation basically is the same. We have this inertial term with some centrifugal terms, damping term, and we have this nonlinear stiffness, time dependent, but here we have plus sign. It means that we actually increase stiffness when we pull it. It's like guitar string. When you pull it, the tune goes up and not down, which is pretty reasonable to think about it. So here it's positive, and this is a result of the model. So we have these parametric curves. It behaves canonically as parametric oscillators. Now it's more interesting. So this is the devices. They're relatively big, a 2 millimeter long beam. This is a frame. I will show the experiment. Maybe it's best. So what you see here is the following. This is this is the beam, this is the frame, this is the electrode, and it will move in this direction. So what we do, we sweep the frequency slowly, some specific amplitude of the voltage, as the frequency which is twice resonant frequency. This is all the parameters, the frequencies, sweep time 60 seconds. This is the voltage, and you can see what happens. So at the beginning, you don't see any motion, and it's totally still. But at some time, it just explodes. So this development results very, very fast. It's just few frames. And after that, it decreases slowly when you continue to increase the frequency. It's just one example of it. And if the image prosthesis, we just use image tracking, very simple in MATLAB, you can build these resonant curves and this so-called parametric torque. This is a stable area where the vibration decay, and this is unstable area where the resonance develops. Okay, so it's somehow experimental results of this kind of the device. What happens that I am slowly going to erase now, that if you now think about not one device, more of them, you want to have array of devices. In order to synchronize them, they should be exactly the same frequency. But it's not easy to do because due to fabrication, every part actually has some small differences in geometry and so on. So actually they don't vibrate. It's not obvious that they vibrate together. And when we try to actuate this kind of tuning for device, is it running? Yeah, I have it here. Yes. So you will see that actually they're not vibrating together. So first this guy vibrates. Amplitude here is huge. It's about 150 microns. And this guy doesn't move too much. It moves a little bit. But after that, this part starts to vibrate, which means that it's not easy to synchronize them. And in this array that I'm going to show, we actually succeeded to synchronize a very big amount of these devices. This is some simplest array which contains only 2 elements. Now, to reduce the footprint of these devices, so we came with another approach to excite this parametric resonance by excitation using fringing fields. And the idea is the following. If you have a beam surrounded by electrode, and everything is made a single layer. So it's the same layer of the device. You have one beam, it looks like COM drive, but it's not COM drive, the beam deflects out of plane, as it's shown here. If you think about it, if you have this beam in a totally symmetric situation, the fields are symmetric, so the net force is 0, if everything is ideal. But if this beam goes up a little bit, we break the symmetry of the field, and we have restoring electrostatic force here. So this electrostatic force pulls it down together with the elastic force. If you plot the dependence between the force and the deflection, the force is 0 at the center. After that, it goes up, and after that, it decays. So this force is symmetric, and it's linear in this region, of course. It has a maximum, and after that, it decays. It starts to be nonlinear. Okay, so this force, first of all, is electrostatic. It's a kind of stiffness, but here, in contrast to regular or most known actuator, it's actually stiffening and not softening. So this spring is not negative, it's positive. It's positive stiffness by any means. Now, because it's voltage dependent, we can make it time dependent, and we can. So this is different approaches how it was done. Something in this area also with COM drive actually works in a sense in a similar way, but in our slit it's just flexible beam. If we build model of this device, finally we have this kind of equation, which is in a sense the same. So we have this beam part which is the same, and we have this electrostatic part, but now we have this plus sign because it's positive. It's really elastic foundation or elastic spring. And when we build reduced order model by Galerkin, we can arrive to one or more ordinary differential equations with this electrostatic term. So this function, actually one of possible fits, we use default fit, this one of them, which fits this electrostatic force. And this is the final equation, which is for small deflection, which is canonical parametric equation with this time-dependent stiffness. We can also write in terms of delta and epsilon and have the same behavior. And this is a result of the model. So we have this typical resonant curves here. And this is frequency, right? This is frequency, and this is amplitude. And for different voltages, this resonance evolves. And this transition between no resonance and yes resonance is very sharp. And actually, it's very attractive for using sensors. And recently, several papers appeared suggesting to use the jump for sensors. Because if something happens, this jump moves in frequency. It's just transition go on go. It's digital. You have response or zero response. So it could be very, very sensitive for detection of mass, stress, biodetect, and so on. So people start to explore this also for sensors. And this is how the device looks like. So we have the beam, the electrode, it's SOI. There's a big cavity under it, so it can develop large amplitudes. The quality factor in there is about 150. And this experimental result, so again we have this very consistent with the model. We have this frequency, the velocity response, and this parametric tone. So in terms of frequency and voltage, we've seen this so-called parametric tone. We have this parametric resonance. Outside we have nothing, so every disturbance decays to 0. Okay. Also, because it's spring, I just said in passing that because the spring is voltage dependent, you can actually tune it, which could be also very good for sensors, because you have some tunability. In fabrication, nothing is certain. It's very difficult to fabricate something exactly the frequency that you want. So here, by applying voltage, because it's again the spring which is voltage dependent, you can tune frequency in relatively large region up to 10–12%, which is pretty a lot. And I would like to emphasize that in contrast, all this big actuators, a simple beam, you can downscale it actually to nano size. It's very, very small. So for this kind of design, it's different. It's different from other design because it's just very simple cantilever. You can downscale it. It could be actually sub-micron size. It's the same physics.
But you haven't done it yet.
We did it, but we don't have it completely accomplished to publish. But we did it. You can do this at much smaller scale, of course, because it's the same physics, right, up to very small size. Now arrays, and after that started to think what happens if you take more than one beam and put them into arrays. And arrays is a very hot area, I should say, and at least there are several applications where they are very attractive. One application which will be probably closer to your activities here is biosensor or mass sensor, because if you have many beams, you can use some selective identification of different analytes, so you can some average statistics and improve noise and so on. So people started to explore these arrays for sensing, and there were several works here, especially if you can have localization, for example, so you can control, if you have many beams, which one vibrates, just address it individually without necessity to bring individual wire to every one of the beams. It could be actually very useful for sensors. Another application, RF filters, and also in diffractive optics. If there are many beams, you see several beams vibrating, so you see these black lines. As every black line actually beam which vibrates more than other beams. Okay? So the application of it, but also there's interest because they exhibit very rich dynamics, and from the nonlinear dynamics point of view on, or experimental nonlinear dynamics, yes.
For the nano-sized particles that you've made, what frequencies do you need to? What frequencies are they excited at? I'm assuming that it's not kilohertz anymore.
It's much higher. I mean, the highest that we measured in this cantilevers was 100 megahertz, but it could be higher. But 100 megahertz, it's about 3 micron long beam, very short. Cantilever about 200 nanometers thick. So they're in tens of megahertz range, especially if you go to higher modes. The highest MEMS, I mean the highest oscillators, I think was about 40 gigahertz area, but they are solid-state disk oscillator, not beams. In this kind of device, it's tens of megahertz. Is
you have to fabricate them with ion beams or something?
Yeah, this size usually we fabricate with ion beams. Yes. Cool. But even today in optical lithography in steppers, you can go to tens of nanometers range in fabrication, maybe 100 nanometers. So it could be downscaled. Okay. Now, if you speak about arrays, all these arrays, all the works published so far, they could be subdivided into two groups. The first group, I call it mechanically coupled arrays. In this case, you have many cantilevers attached to so-called overhang. So this part of the plate suspended in air, so it has some compliance. And due to this compliance, all these beams are intercoupled. So they behave collectively. You don't excite every beam individually, you excite the collective modes. Right? And the main interest here, in addition to application, to look at the collective behavior, dynamics, propagation band, and specifically localizations. So here, there's several works, mainly by Sato group. So this is time, and this is site. So this is beam number 1, number 2, number 50, number so on. And you see this black part means that these several beams oscillate, and all the other beams don't oscillate. So this is a localization, so-called soliton. There's a lot of activity in this localization because, again, from application point of view, if you can address individual sites just by changing frequency, and it could be useful for sensors, and also it's very interesting from the general physics point of view. So these devices, they have so-called propagation band, so they start to oscillate starting from certain frequency, and they stop to oscillate on some other frequency. So they oscillate between these two frequencies, and there is a band gap above, a band gap below. Right? And this curve, of course, depends how many beams, what's the levels of coupling, and so on. And sometimes they demonstrate the solitons. Now, in all these mechanically coupled devices, you cannot tune them. So they cannot make them time dependent because the coupling is defined by the geometry. Once it's fabricated, it's like this, you cannot change anything in it. So people try to change laser on it, but basically they are not tunable. Yes? And if you look at the equation of it, it's actually equivalent in a sense to equation of elastic string, it's just discrete contour part of it. So you have this so-called on-site stiffness, this is stiffness of the every beam. You have inter-site stiffness of the coupling, and this minus sign means this actually the string, so it supports traveling wave, it has real eigenvalues, it's a vibrating system par excellence. But coupling cannot be tuned. Another group of works, the electrostatical couplers, it was pioneering was the books and Lucas in 2002. They have many strings as they interact through parallel plate capacitors. In this case, you can tune everything, you can excite them parametrically, but the story is that here we have plus sign, so the spring is negative, so they don't have real eigenvalues. It's not dynamic system, it cannot support not traveling wave and not normal vibration, normal sense. Okay? So we started to see how we can match between the two, and we came up with this kind of design. So we have this kind of device, which look actually very similar to interdigited electrodes for surface acoustic wave, the COM drive. And one of the reviewers said, okay, it looks like COM drive. Yeah, but it's totally different. It's not COM drive because every beam moves out of plane, and it interacts, which its closest and probably even not closest neighborhoods. And this part is coupled mechanically through the overhang, and this part is coupled mechanically through the overhang, but this part is coupled only through electrostatic field. So where the field is zero, the right-hand part knows nothing about the left-hand part. They're totally separated. But once we apply the field between them, they start to be coupled. And the question if we can synchronize them, if we can produce some kind of collective behavior and see what happens here. Okay. So again, usually I try to do some modeling before we do fabrication, and at least to see what happens, because the math here is pretty interesting. So if to say a few words about the model, so every cantilever is modeled as a cantilever, and this is electrostatic part. Now it depends on two neighborhoods. So we have here n+1 and n-1. So it's some kind of 3-point system, and this is electrostatic coupling. So this part is just cantilever. It's not intrinsic, but this part is interesting. And this function is actually the fit of this same electrostatic force that we had as a single cantilever. And we use, of course, Galerkin to make it reduced order to have some finite number of differential equations. So we just multiply that by some mode function, integrate it, and we arrive at the equation, which is a system of ordinary differential equation. Every u here is a deflection of the end of the beam. And this is inertia, this is damping quality factor, this is on-site stiffness, this is some nonlinear part of it, and this is all this coupling. So this is mechanical coupling due to overhang, and this is electrostatic coupling due to electrostatic field. Now, how we calculate this? For the electrostatic coupling, it's relatively simple because electrostatic field decays very quickly. We can consider only closest neighborhood. But for mechanical coupling, it could be more complicated because actually the coupling is not local. So the beams through the overhang, it interacts not only with the closest beam, but for some more beams. So what we did, we just run finite elements, and I put it in an appendix, so it will be a question how we did this. I can specify on this, but here I just will say that we run finite elements, and we extracted this inter-site coupling in full non-local interaction matrix from the finite elements. This example of the mode. So how it looks like from specific mode of this array. So this is mode number 3, this is mode number 11, this is mode number 30, and this is propagation curve. So this is the mode number, this is the frequency. So this is propagation band. We have some band gap below it. It's normalized to the lowest frequency. We have band gap above it. The points are finite elements, and the pink line is our reduced order model, which fits not bad, I would say. So we can somehow use it in our reduced order model. And now, if you think about mechanical meaning of this model, it looks like that. We have this mass. It's actually a mass and spring system. Mechanically, every beam is attached to the substrate. So we have so-called on-site spring, this guy. Every beam is attached to every second neighborhood because mechanically, if I go back a little bit here, so every beam is attached to every second beam mechanically. And it attached to every first beam electrostatically. So this is why it's a little bit strange system, but it's how it looks like. So it's attached mechanically to every second beam and attached electrically to every first beam. So this is analogy of this spring is electrical, is time dependent. These two springs are constant, are steady, and they are not time dependent. And when you have this kind of mass spring of systems, the first thing that we think about, what kind of wave can propagate here, and we do so-called dispersion analysis for it. We substitute this traveling wave solution into this equation, and we counter this dependence between the frequency and the wave number, which is so-called dispersion relation, which relates the length of the wave with the frequency of the wave. So it actually could be voltage dependent. For 0 voltage, we have this kind of the curve, and this is the shortest wave which can propagate. It's defined by the distance between every second beam. But when we start to increase the voltage, we change the dispersion property of it, and when the voltage is above certain area, there is certain threshold here as well, it starts to be shorter 2 times, because we have now every first neighborhood interacting. So this is propagation curve of it, and for relatively reasonable voltage of 100 volts, it could be very, very large, this propagation. If you see this mechanical propagation area, it's only 10%. But the electrostatic propagation area could be 5 times more, so the tunability of it is much, much more significant, which is good for application in some sense. Now, as I said, it's possible to see some kind of string on the last foundation. I maybe will not go too much into mechanics of it, but I just will say that if we expand every deflection, every mass into Taylor series, and we take on the long waves, for long waves, it behaves, it starts not to see every individual mass, so we can see it as some kind of continuous system. So we arrive to this equation of a string. So what we see here, this is actually a string, like D'Alembert string. But we have all this nonlinear part, which is some kind of nonlinear tension. So if you think about a string, and the tension force of the string is time dependent and nonlinear, and it looks pretty crazy, but it may be not too much. So this is a force, the tensile force of the string, and its stiffness is defined by this thing, by this force. So it looks like this. This is the constant part of it, and this is all this nonlinear coupling, and one of them is voltage dependent, time dependent, and we have plus here because again this is real string, this is real force and not negative one. Okay. Now experiments. From simulation point of view, if you take just mechanical model and we drop all these nonlinear electrostatic terms, we can build this dispersion curve. This is a number of mode or wavelengths, possible to say, and the frequency. So we have this propagation band between 23 kilohertz and 26 kilohertz. Everything is dimensional here. Now, if you just simulate it, we just start to see frequency, and we see how the shape of this chain evolves. So what we see in this plot, it probably requires some explanation. So this is the beam number, and this is the frequency. So we did here, we run the analysis, we arrive to steady state, we measure the amplitude of every one of the strings. So we have 200 strings here, the color is the vibrational amplitude. Now we change the frequency, we do it again. So every row in this matrix, it's actually a different frequency. So this is some kind, it's similar to the real-time spectrum analyzer if you look at the spectrum from above. Right? You see this color picture, how the spectrum evolves. So it's exactly what you see, but this one is simulated. Okay? So we see the first mode, it's very big valley here. And after that, higher modes start to evolve. So we have here more modes and more modes. After this and this is a propagation band. So we see this area, this is a total map which actually visualizes directly the entire dynamic of the story. Now, this is classical, probably it's not usually presented in this way, but it's, of course, very, very known, the vibration of string, that's classical problem. But if we add now this electrostatic force, and we start to do the same, if you plot the dependence between the frequency and the deflection, it starts to look like this. So we have these jumps. Every jump is parametric resonance within these propagation bands. And this appears during interaction. If you do the same trick, if we sweep now the frequency, this is direct simulation. We have 200 beams here. What happens is that, first of all, nothing here. After that, already higher modes appear, and the jump between the mode and the mode occurs abruptly. So we don't have this slow evaluation that all the modes are evolved. We have some sudden transition between this mode and this mode, and if you count that there are mode peaks here, that here. It's another mode. So there is synchronization within this area. After that, it jumps to another mode. And after that, it jumps to another mode, and so on. So it's a relatively strange behavior which is not really observed before, that we have this synchronization in the mode as it jumps to another mode, which happens here. So we try to see if we can see this experiment. So this is a device, and device is fabricated in Cornell with help of Rob Bldg. So how it looks like, we have 100 beams here, we have 100 beams here, they are attached to this flexible anchor. Here they are attached to the flexible anchor. We have this overlapping area where all the electrostatic actuation and electrostatic interaction takes place. Okay, and we have two electrodes at the end, just to we grounded them, just to not to deal with them, but to have some predefined force here at the end. Okay, and we have very big cavity under it, so they can really vibrate up to large amplitude without any danger of stiction, electric shortening, and so on.
How big is the silicon?
The silicon is, we have several variations between 3 and 5 microns. So it's SOI, thin SOI. This specific, I think, is 5 micrometers, but we also operated devices with 3 micrometers, relatively thin. And the beams are between 300 500 microns long.
Yeah.
Up to 7. So it's relatively big. This is about 4 millimeters device. So in order to see the entire array in an optical microscope, you have actually to have some very low magnification, because usually probe station you have relatively large magnification, not suitable for it. So we bought special lens, 1x, just to see the array, because otherwise you don't see some small challenge. Okay, so this is the setup. So we basically do two things. We measured by laser Doppler vibrometry some individual beam. We cannot measure entire system. We measure individual beams, and it comes from LDV to network analyzer, and also we drive it through network analyzer and through amplifier. It's gain 100 amplifier. It's variable gain. Also we monitor on the scope, of course, what we are seeing. But also we take images and movies of the array to see if we can see some collective behavior. And now some movies. So how does this look? What we see here is the following. You see the array, this parameters array. This is 500 micron long beam. It's about 150 overlap. This is the array. Okay, and we start to sweep the frequency. We start from frequency below propagation band, and after that you sweep it, and we just take a movie from the camera. And what happens, you see that mode appears, and it starts from relatively high mode. And what is nice here is that we start to see how it's possible to see, because it's just regular camera, low frame rate. It's not something special, it's not fast camera. But what happens, the depth of focus of microscope relatively small, and amplitudes are large. So when it comes out of the depth of focus, it starts to be dark. It's actually blur. So it's some kind of so-called sub-aliasing imaging technique that we practically see blur, because we have many vibrations. It's 10 frames per second movie, and this is 20 kilohertz motion. So it just blurs everything, but you see the modes. And you see that starts to be this strange mode with some localization on the end of the propagation band. So this is sweep up. I have a few movies now, so now I'm more in movies. And this is sweep up, this is sweep down. Yeah, so we see this mode evolving. So it starts from shortest wave, where every second beam vibrates, and after that. But what is nice here, if you see that the dark areas are synchronized, and this is the main thing here. That's in contrast to these in-plane devices, they are really synchronized. You have collective behavior, and we end up actually with localized vibration. We didn't have it here, where we sweep from below. It doesn't happen when we sweep from above, because of the Easter edges. We have this localization, which is itself pretty interesting phenomenon. And this is shorter beam. They behave more or less the same, but for shorter beam, the reason that I'm showing this, the shorter beams, they are stiffer. And because they are stiffer, they have, of course, difference in fabrication of them, and they don't have the same frequency, necessarily. And in this shorter beam, you will be able to see that actually they don't vibrate, so you see that's not the same. They are synchronized by less, because there are more difference between, so the voltage is not enough. There is some synchronization, but it's less pronounced than in the previous case. Okay, but still, when the wave became shorter, they synchronized more. So it's really electrostatic synchronization, all the entire collective behavior of this thing, and this is the modes. Now, what we did after that, just to see the entire picture, we did the following. First of all, this is several snapshots. So this is a localized wave, which cannot appear in a linear system, in principle. And this is the first mode, the second mode, the third mode, and so on. So this white curve is actually gray level. If you take an image, you just upload the profile of the gray level, you see these figures. Now, this gray level, it's not quantitative. We cannot measure the amplitude of vibration in microns, so in nanometers, but we can visualize, and at least we can see the wavelengths. Now, after that, if you just measure the distance between these peaks to see the wavelengths, we take one row of pixels from every frequency. So this frequency we take one row in pixels. So in this movie we split it into frame, and we take one row of pixels from every frame, and we put it together into one image, into one matrix. So finally we came out with this kind of image. So here this is the beam location, and this is the frequency, and you just see what happens when you start to see the frequency. Nothing here, we are below the propagation band. Now this is the first mode, the second mode, and we see the jump. Between one mode to the second mode, there is this very sharp jumps. Now if you plot the wavelengths of every one of these bands, and within every band we have this synchronization as a function of frequency, we have this dispersion curve, experimental dispersion curve, and what is nice here is that we have these jumps, and these jumps is just not because it's BMP image with very low resolution, it's real, it's physical jumps between the modes. Of course, we play it with the frame rate of camera just to verify there's not some stroboscopic effect, it's real. Okay, this kind of behavior, and we did many experiments just to verify there's no artifacts. So two different beams and two different cases. This one starts from localization, and this is how it looks like. I would say that in the sense it's similar to simulation, at least qualitatively. But we also wanted to see, again, that it's not some artifact, but to measure the real response. So we did this using a laser Doppler vibrometer. For small voltage, if you remember, there is a threshold. So with the amplitude of actuation below the threshold, we don't excite parametric resonance. Theoretically, we should have 0 there, but there is some direct excitation due to fringing fields and substrate and the wall of the cavity and even noise. So it's never perfect zero initial condition. So when we excite it below this parametric threshold, we have some kind of linear behavior. So this is linear resonance, more or less within the propagation band. And this is the result of the pulse. If we just give some short pulse or some burst of voltage, and we build a spectrum, we have real-time spectrum analyzers, we can do this. So we have this pulse, as we said, more or less the same region of frequency. This is linear behavior. Now, when we increase the voltage above this parametric threshold, we start to see these jumps. And we see that it looks somehow not chaotic, but not so arranged, these peaks. But every peak is actually jump between the different modes. But in order to see that actually we have something that we understand what's going on, we did the following. We took this movie, and we measured simultaneously by LDV, specifically within this area. So these numbers, they are number of beam. Here's the beam number 100. And if you move a little bit aside, it will be beam number 90 and beam 95. And so we move to both sides of this peak, and we measure the spectrum using LDV, and you see that all the jumps are actually consistent with this jump. So it's real behavior. We have more amplitude here than here, and here it's dark, so we have large amplitude, and here it's white, so we have small amplitude, so we have some amplitudes here. Okay, so this somehow, at least partially, convinced me that this is the behavior of this array. Now, here the question arises: is this coupling? It could be actually it could be a result of air, because we operated in air. And this coupling could be a result of acoustic interaction, just damping and not electrostatic. So we also used to drive this in vacuum, and in vacuum the voltage is very small. But if we just drive these devices mechanically, so what we did is just put the device in another camera. It was done in Cornell already. So it's another camera, another color, in another device. But what happens is that if you put it on piezo, this is inertial than piezo in vacuum. We see that they don't vibrate together. So this, these big spots, we have very large amplitude. The upper side practically doesn't move because the split of frequency, something about 100, 150 kilohertz, is just not synchronized at all. Okay, and if you do the same story with the modes look like this. So you see there's a very, very long first mode, the second mode, but we don't have these jumps. It's more or less behaves linearly as it should behave in this mechanical array. I should also say that we used to drive them in air. And in air, you clearly see that you don't see the synchronization if you drive it on piezo, even with high damping. Now, I calculated recently the order of magnitude of forces. It turned out the damping force is a viscous Stokes damping force. It's about order of magnitude smaller than the electrostatic force, and the acoustic force 2 order of magnitude smaller. So I pretty believe that this damping is mainly due to electrostatic actuation and not due to air.
Well, it's not like a tuning fork, and the air is propagating the sound from one portion of the...
Yes, it does. It propagates. But again, the level of force is very, very small. And in tuning fork, they don't have the same frequency. But this part of it, these beams and these beams, they don't have the same frequency. They're different. So it's not enough. It exists. Of course, there is acoustic interaction, but because there is a split in frequencies, it's not enough. Not enough. Again, we tried to drive it on piezo in air with very large amplitudes. You see very, very big amplitudes here. It could be tens of microns, 20, 30 microns for these beams. And still, they don't vibrate together. So this coupling is essentially electrostatic, and also when you drive it even in air mechanically, you never see localizations because it's linear, or it's slightly nonlinear due to nonlinear air damping with these gaps, but it's still not the same level of nonlinearity as you can have in electrostatic actuation. This is the story with this array. So what I'm trying to say is that it's a very, very interesting object. I started to work with it some time ago. I cannot tell exactly now what could be the best killing complication for this kind of device. It could be filter for RF. It could be biosensor, mass sensor, because you really can control these localizations, and they're very, very sensitive. It could be used actually, it's actually a known idea that there's a thing so-called vibration signature. You have this pattern. It's this pattern much more sensitive to anything if you compare it just to the linear frequency of the individual beam. So by monitoring these patterns, actually, you can measure a lot of things. And in order to be able to do this, first of all, you have to understand how this thing behaves. And this is was an attempt to do some contribution to this area, to understanding the physics behind this relatively complex nonlinear behavior of this kind of devices. And again, I'm continuing to work in this direction, and we measure different kinds of designs around the same idea, and to see what we can understand in these devices. Acknowledged, so part of the devices were fabricated in Tel Aviv, so we have our own facility we can fabricate there. And I would like to acknowledge, of course, this Mary Upson visiting fellowship that I spent some time in Cornell. And we also have some research grant from about parametric resonances from EU, which supported partly this kind of research, parametric resonances. So thank you very much for your attention.